Hello guys, welcome back to my channel, and today I'm back with another one of my projects that I want to showcase. This time I built a fully fledged modern search engine with all the bells and whistles like RAG, chunking, pre-processing, etc. You might be wondering why I built this project. Well, it was very simple. In today's day and age, I see people building RAG apps and many cool things using AI, but I did not understand what goes inside those apps. Like, what is going on, what is exactly going on when we do RAG. I just wanted to have a deep understanding of all of these concepts. So, you know, what is the best way to learn? For me, it's just hands on coding, and I decided to build my own search engine to understand what the hell is actually going on inside these RAG engines. Now I'll just walk you through what I built and explain each and every concept as best as I can. Now, this is the architectural diagram of the whole project. So I'll just walk you through it. It's very simple. First, we get a user query. Then there is an optional query enhancement, and I achieved queries enhancement by using LLMs. Query enhancement basically means like correcting spelling mistakes of the user, making the user query more expansive and rich in keywords. So it is easier for the search engine to get a good result. Then there are two types of search which are going on. First is keyword search, and second is semantic search. Keyword search, as the word suggests, specializes in searching proper keywords. Like if you search the movie Revenant, it will get you the movie Revenant precisely and accurately. This is not the case with semantic search. Semantic search the feeling or the synonym, like friendly, family friendly movies, etc. They are not searching for the keywords. They are using vector embeddings to search similar things to the user query, which is stored in their database. Then I combine both of those in hybrid search using there are two types of hybrid search, weighted and RRF. Basically, hybrid search just combines the two types of searches and gives a combined result for the both, so that we don't miss any keywords and any semantic search results which can be relevant. Now, re-ranking, you can use cross encoders or LLMs to do re-ranking. Re-ranking basically means sorting the result from worst to best after getting the result from hybrid search. Again, this is also an optional layer, which is evaluation. You can evaluate the search result. I wrote a test for it which judges it by precision, recall, and you can also do manual evaluation. I did something smart which I feel like helped me a lot. Was I used an LLM as a judge. Now, to now the main part, augmented generation, which basically means all of the search result that you got, you pass it to an LLM to generate whatever you want according to the user query, like a summary, citations, etc. This is the main crux and what makes these search results so powerful in modern day and age. This is what RAG is. After that, we just get the final response. So now I'm going to explain keyword search. First of all, what you are seeing on the screen is the CLI tool I built for keyword search, which have different arguments you can pass through to get simple things like index, like you can build your data using the build command, tf to get term frequency, which I'll get into what is term frequency, idf, how to get tf idf. All of this I'll explain in a minute, but this is, I just want to show the tool I built for it. And here I also built some utility functions for it, which is basically here. They are search. This is the TF IDF utils, which does all the calculation for you. This is text pre-processing util function, which is very important because it tokenizes all of the words and the paragraph you get, and that is the basis of keyword search. Okay, so I'll just move to the keyword search CLI and explain each term. Okay, before I move forward, this is the actual implementation and the class of the keyword search. I named it as inverted index. It contains index, which contains basically the index of all the documents. I am using movies as my data. Docmap mapping each document ID to the document itself. Term frequency. Term frequency is basically the number of times a word occurs in a document. Suppose the word awesome. Awesome occurs 5 times in the script of Revenant, for example. Then awesome has a term frequency of 5 with respect to the Revenant document. It's as simple as that. And doc length is basically having the like storing the length of the document, of each document. Now I'll get into the meat and potatoes of it. I already explained what TF is. I'll like to explain what IDF is. Let me go back here. Yeah, IDF. IDF is basically kind of an inverse of TF. It searches how rare a word is in all of the documents. Suppose the word iridocyclitis occurs like once throughout the whole data set. So if someone searches iridocyclitis, it's easier to for us to get like which document contains iridocyclitis, because it's just one. This is like not possible. This is an ideal case, but this is the idea behind IDF. So now what we actually do is basically combine and multiply these results, both TF score and IDF score of a word, and the higher the score is, the better. Now you might be wondering, what is this BM search, BM25 search? Yeah, what is this BM IDF, BM25 TF? There is one problem with TF that it fixes. The normal TF IDF algorithm is very easy to cheat. For example, I put a lot of I's, awesomes, etc. in my document, so that whenever someone searches awesome, my document is prioritized, even though there is no meaning of me putting all of these awesomes in my document. I just did it to make it optimized for the search engine, TF IDF search engine. This creates a problem, obviously. This is what BM25 TF IDF fixes. It basically penalizes more occurrences of a particular term, which is basically known as terms saturation. And this basically also is applied to IDF, it normalizes and saturates the word, and then we combine both of them to get a BM25 TF-IDF, which is basically the same as TF-IDF, but more robust, because you can't really you can't easily cheat it, because more words has a very less impact on the search result. Now I'll give you a practical example of it by running the CLI tool. So I can just do it by running this command. Bear DiCaprio, obviously referring to Revenant. It loads the index, etc. And here is it. The Revenant is the first thing we get. This is the power of keyword search. Now, as you might have guessed, keyword search has its disadvantages. It is only ever good to search with keywords, but users don't really give proper keyword search. Suppose if I was searching bear movie in forest, like for example, again referencing to the Revenant, it won't give me Revenant because it will search bear keyword, forest keywords, and probably give me some other document which have those keywords, right? So this is where keyword search fails, but it is also very advantages in the sense that it is very less like computational heavy. You can do searches very quickly with this. Now I would like to move on to semantic search. Semantic search basically covers the weakness of keyword search, and it searches for semantic meanings like family friendly movies, etc. But it is not as good as keyword search in searching for like actual keywords. If you search the Revenant, it won't give you Revenant, or at least won't give you Revenant at the top. And it is also computationally heavy, very computationally heavy. So basically the idea behind semantic search is we break the document into smaller chunks, which makes sense. There are many chunking algorithms. If you want to go through all the chunking algorithms, you can easily go through it in my code. I have put the link in the description to my GitHub. Okay, so basically it breaks the documents into chunks, and then we embed those chunks. And when a user gives a query, we also embed and convert it into a vector as well, and we then run a cosine similarity algorithm, which basically tells us whether it is similar to this particular these two vector embeddings are similar or not, and if they are similar, we return them. This is like the class implementation of semantic search. There are two classes here: semantic search, which is a semantic search without any chunking. I did it to just find out what is semantic search exactly, but this is not very efficient because like without breaking up, you are basically converting a whole document into a vector space, and you lose a lot of meaning because of it. I'll just give you a practical example of it. First of all, I am going to search what I searched for in keyword search, and you will see that it won't give me a very good result. So I searched for Bear DiCaprio. It gave me Legends of the Fall, Beastmaster, Great Bear, Ted, and Unfinished Life. So basically something which contained bear, like try to search the semantic meaning of Bear DiCaprio. So let me search another thing which has a semantic meanings. Let me search family friendly movies. See, now it gave us, I don't know how to pronounce this. I don't know, like I won't even try to pronounce it, but through the description you can say that it is a wonderful slice of life in rural Italy. It is a family friendly movie from the description. It is like it also gives us this a story about two private investigators, uh, Winnie the Pooh, Pride and Prejudice, etc. So as you can see, it gave us all the family friendly movies. Yeah, so now let me move to hybrid search. As I told you, both semantic search and keyword search has their advantages and disadvantages, and hybrid search basically combines the advantages of both and disregards the disadvantages. So before I move forward, I need to touch the on the concept of normalizations. We normalize the semantic score and the keyword scores because they both produce scores in vastly different ranges, and the only way to bring them in, compare them, is to bring them in the same range, and the way of doing that is normalization. So it's very important that we normalize it. Now I'm going to go through the first type of hybrid search, which is weighted search, where basically we perform both searches, normalize the scores, and then basically combine the scores using this formula. Alpha here is a constant. Okay, we combine the scores and then we return the result by sorting after sorting it in descending order. Now I'll go through RRF search, where we don't have the scores and we don't have to normalize anything, but we do have the rank of the documents, like on which order they are occurring in their respective searches, and then we combine the rank using this formula. Like for example, if I want to search for family friendly movies, for example, I'll just search for this Dinosaur Park. There's a limit. I also had many tags here which uh, helps me evaluate and debug, etc. Enhance tag is basically for uh, query enhancement. I can show you the query enhancement here. Yeah, this is the query enhancement file. I am using LLMs to enhance my query. You can also rewrite the query, but right now I am trying to enhance it. And also there is an evaluate tab. I'll remove the debugger tab because it's not needed right now, and you just see what it returns. Yeah, as you can see, it returned the result, and the first thing which I was looking for was Jurassic Park. So let me walk you through what is exactly happening here. So basically, first Dinosaur Park is changed into Jurassic Park Dinosaur Escape, which is like a very good query to give to the search engine. And on the basis of this query, it gives us the result by performing both semantic search and keyword search. Jurassic Park, then Carnosaurs, basically all the dinosaur related movie, and after that I gave it the evaluate tab. Evaluate is basically passing the result to an LLM, and again just making the result more robust. As you can see, it is giving a score to all of the movies which were present in the search result, and telling it that Jurassic Park matches our requirements the most. If the wizards matches our requirements a little bit, and rest doesn't. Now before I move forward, I want to touch on the re-ranking methods that I have implemented. First is re-rank individual. It basically goes through each movies in the search result and returns the re-ranked list and tells us which is the best match for our query. Second is batch. it like basically processes all of the result at the same time, which is like saves us time and like LLM tokens. I'm using LLMs to do re-ranking here. And third is cross encoders, which is faster, but it is not as good as LLM re-ranking. It basically it search for similarities. So I'll run the same query, but this time I will pass a re-rank. I'll use batch. Now this is the result that was returned while after using re-ranking. It is very similar to what was returned before using re-ranking, but that is because the query was so good that it didn't read re-ranking. Now I want to just briefly touch on how I actually evaluated. As you saw, one of the evaluation I did was using LLM, but I also did a lot of manual evaluation. I also created a golden data set, right, of the queries and the relevant documents I was expecting, and then I calculated the precision, recoil, and F1 scores and displayed it, so I have a better idea of metrics and how my search engine is actually performing. You can learn about precision, recoil, and what they are exactly by reading about it in my GitHub readme description of this project. So let me just talk a bit about multimodal search. As you know, people don't just use words anymore to search, they also use images. That is where multimodal search comes in. The idea behind multimodal search is simple. Multiple models working with different data types to produce a search result. It is as simple as that. So this is the CLI tool I built for multimodal search, and this is the actual implementation where search with image uses the image path. Let me show you the image which is being used. This is the image of the movie Paddington. Yeah, so this image is being used, and we also get a query from the user, and then first it embeds the image and runs a similar cosine similarity algorithm using the text embedding. I'll just run it and you can see what is actually happening. UV run CLI multimodal search. It will give the name of the movie. Yeah, now the multimodal search has returned the result, and as you can see, the first result it returns is Paddington. So let me move on to the best part about this project is augmented generation. Basically, now that we know how to get the results from a user query, we pass it through an LLM to complete our RAG pipeline. Now we can do many things using an LLM, like generate a response, generate a summary, generate citations to uh, give credibility to the answer, to the response, or answer user questions. It is as simple as that. Like, this is the part which makes modern search engines so powerful. So that is it for my project. I know it's going to be a very long video because it has so many concepts that I needed to cover and cover properly. And I still feel that I did not cover it in as much in depth as I could have. But if I did, the video would have been like, I don't know, an hour long, and nobody wants to see that. So yeah, I learned a lot building this project, and I hope you also get a deep understanding of what is happening inside a RAG system when you actually do a search using LLMs, and just have a very good understanding, a very deep understanding of all of these concepts. I hope this video is helpful for you, and if you like the video, press like. If you want to subscribe, please just subscribe. It would be very helpful, and if you can, leave a comment down the video and tell me where I can improve, and just any feedback would be very appreciated. that is it from my side. This is Sparsh signing off.